So it's 11:45. I hope you can hear me. Any answer? Yeah.
Good evening and welcome back to the last session of PhD 20. And this last session is chaired by Professor Reber. And I hand over the session to Professor Reinhardt.
Yeah, thank you very much. Can you hear me? Can somebody hear me? I think my microphone should work, but no answer. Anybody can hear me? We can hardly continue in case I don't know this. Can someone? Okay. Thank you. Okay, very good. So before we start our next and last lesson with the talk of Taras Kravetsky, I would like, I have a small duty to do. So I would like Priya Maheshwari to come to any camera, please. Priya, be so kind. Yeah, okay. Priya, you're secretary here of our conference, but at the same time today it's your birthday, if my notes are correct. Is it okay? So therefore, I would like to congratulate you to your birthday. I wish you all the best for your future. I wish you good health in these pandemic times, and I hope to meet you later again, or not so late. I hope personally. So Priya, happy birthday. Okay. Yes, thank you. Okay, so let's come to the scientific part of this last session. So Taras Kravitsky was already announced for the very first day, but for some reason he couldn't do it, so therefore we have it now. Taras Kravetsky is associated with the Strohobych Ivan Franko State Pedagogical University in Drohobych, I'm not sure whether I pronounced this right, in the Ukraine, and he's also in Lublin in Poland. Actually, he's Polish, but I think his main place to work is in the Ukraine. So he's interested in the study of radiation-induced defects in solids, structures, defects, and properties of amorphous materials, and especially, I think, of polymers using positron annihilation. Talk today is free volume characteristics of photocross-linked polymers as holding matrices for construction of amperometric enzyme biosensors. Oh, complicated title, Taras. The floor is yours, please. Go ahead.
Thank you very much. I cannot switch my video, start camera. Thank you very much, dear Chair, for my introduction. And please tell me that this my presentation is seen or not?
No, not visible. And your video is also not visible. But I mean, you can just stay there with the audio. That's okay. And your face is maybe not so important. But we have to see, of course, your talk. It's not yet shared. Please try to share it. Yeah, now. Okay. Yeah, fine. So we can start. Thank you very much. Taras, there's a problem with your audio. It sounds like tape with a too high speed. This is really strange. I'm not sure. No. I think, Taras, this does not work. I mean, we can see in a nice way the content of your talk, but the audio does not work. Is it? Okay. No, I mean, I think you should do it live. I think it's not live. You recorded this audio, but this speed is completely different and wrong. So please take the microphone and just make you talk, okay? But no, sorry, audio is not okay. Taras, you should use your a normal microphone. It does not work as you do it now. There's the speed of the audio is much too high by a factor of 5 or so. I'm not sure. So this no, we cannot follow this talk this way. No, sorry, it doesn't work. So it's too fast. Taras, you used your microphone already, so why not using it once again with a normal audio just from the microphone? I have no idea how this happens. It's impossible.
Excuse me, Dr. Sagasri, can you unshare your slide and again we'll try? Kindly unshare your slide first and we'll try to do it.
Taras, can't you use the microphone simply and speak to us? So there's something wrong with your recording. I guess you did the video or whatever, but the speed is wrong. So we cannot understand you. But just show your slides and take a normal microphone as you used it before, and that might work. It sounds great, Taras.
Dr. Kavetsky, are you able to listen to us?
Message. Chat.
At least reply in chat.
You can write now.
Yeah, Taras. As I said, your transparencies were nice, but your recorded audio is the wrong speed. So we cannot listen to this. I mean, why not using just your transparencies and the normal microphone, and you tell us what you want to tell us? Naja, so I have asked the organizers, we can do it maybe in such a way that we start with the next talk. This is Dr. Tevari, and Taras can try to solve her problems, and then he can in the very end give this talk of this session. What do you think? Shall we do this?
Yeah, Professor Leonard, we can start with the next lecture, and meanwhile we'll try to get slides from Kavetsky, and if he can present only by audio, we'll try.
Yeah.
Meanwhile, we'll go on to the next.
Okay, yeah. So Taras, please, we make it in such a way, yeah. So we will continue with the session, and in the very end, I will ask you to come up with your talk once again. I think this is maybe the best way. So we have some time now to check everything. Okay, so next talk is by Dr. Tevari from BARC, also Baba Atomic Research Center. And the title of his talk is High Entropy Alloys, New Concepts in Alloy Designing. This is very interesting, and I think I have many questions. And he's an outstanding scientist working as the head of Material Science Division at BARC in Mumbai, and his research activities include development of newer alloys for structural applications at elevated temperature and for higher burn-up structures and related phase transition and structure property correlations in these alloys. Yeah, we are also very interested in this high entropy alloys, as many people in the world do in the moment. Therefore, it will be a very interesting talk. So, Dr. Tevari, please, the floor is yours. Please go ahead.
Good evening, everybody. And at the outset, I want to thank organizer for giving me this opportunity to share some of the work we are carrying out at BARC. Idea of presenting this work over here is that we wanted to use this positron annihilation technique in the development of these alloys. Though I will not, because some of the slides I have eroded because I thought that I had to just present in 10 or 15 minutes time. So you may find some slides are missing, but the concept what I wanted to give was that in nuclear application, the defect generated can be best classified or probed or characterized by positron annihilation. And in this process, we wanted to use a new concept and the new technique to find out how the performance of various materials are there in the nuclear application. But let me start with the high entropy alloys. And see, for any structural materials, if they have to, you have to use them in a reactor, then they had to qualify series of the properties. For example, high melting point. You should have high dimensional stabilities. They should have a very adequate tensile strength, low DBTT, very good corrosion resistance, and this for any structural material these are required. But for nuclear application, you require on top of that few more properties. For example, they should have a very low thermal neutron absorption cross sections. They should show very high resistance to radiation creep and growth. And because of these combination, not many materials, though they appear in many other applications, they are not possible for the nuclear structural materials. The most optimally solutions are found in the zirconium based alloys, and the most common alloys used are the zircaloy 2, zircaloy 4, and zirconium 2.5 niobium. And with the current scenario, when the reactors, now we want more efficient reactor, we have the problem with the radiation related work. So I'm just giving a comparative chart over here where you can see that the conventional reactor temperature is ranging between 200 to 300 degrees centigrade. The advanced reactor we are proposing can go up to 1000 degrees centigrade. The typical life cycle, if I go, it's 40 years. Now we are trying to design reactors for more than 100 years. Now the others, and after when we want to dispose the material in the depository, so before that we were not bothered about and let it decay over tens of thousands of years. Now we are paying a lot of attention to see that within 300 years, the background radiation come to the natural radiation level within 300 years. That is a 3 human life cycle, if I want to say. The damage in the material, on the contrary, is shooting nearly 10 times approximately one order up. From 25 dPa, it is, we are going to 200 dPa. dPa means displacement per atom. That is, each atom has left its position and came back at least 200 times. Now, operation temperatures are increasing, so the stress and so the materials are changing. So the conventional zircaloy were later on in the fast breeder reactor, we tried for austenitic stainless steel. But now we are slowly moving to the ferritic martensitic steel and then to the ODS steel, the sequence shown here, and above then I am trying to show the new materials which are called high entropy alloy. Why these high entropy alloy are very important? Why these alloys are very important is because you can see in a graph which I am showing over here that if you draw a graph between yield strength and the fracture toughness, the high entropy alloys sit right on the top, that they have adequate yield strength and very high fracture toughness, and that is why these alloys are one of the best proposed alloy for future reactors. Now, to give you the basic concept, what happens? See, for any phase in any material system should have the lowest G energy, that is free energy. So conventional way, we were trying to achieve this lowest G energy in form of in reducing the H. That is delta H mix. We want to have the as much as possible to reduction. So what we were trying to do is we were moving from metals to alloys, from alloys to intermetallics, and started going to the structural ceramics, so that you can have very strong bonds between the atoms. But in this process, what we were doing was that we were sacrificing the ductility at the cost of the strength. And that is why structural ceramics, though they show a lot of potential, they still could not be used because the toughness becomes extremely brittle. So another concept was popped in, and that was called the same reduction in the free energy can be obtained by increasing the entropy. Now, how much? That is the question comes in. So the table shown below here is showing that as you increase the number of components, the configuration entropy started increasing. So the typical high entropy alloys are those alloys where my entropy is crossing 1.5 R. So that is why all the elements, all these alloys which form a single phase, by adding 5 elements, classify into the high entropy alloys. Why high entropy alloys is important? They are important because, number one, from theoretical point of view, they do not follow the typical Hume-Rothery rules. They do not follow the phase rules because number of component and number of phases are not coming in proportion. But from phase transformation point of view, if let me draw your attention toward this triangle, see, conventional alloy generally probe to the edge of any phase field. In a triangular phase field transform, any phase field if you draw, so they generally probe only the corner part of this, whereas high entropy alloy hit right into the center of the phase, and that is where they achieve the high entropy. So in the process, what happens? We are increasing the strength without compromising too much with the ductility, and that could be the new alloy systems. Okay. Now, what is the advantage? So we are gaining high strength, we are gaining high hardness, we are gaining high fracture toughness, and if these three properties are ensured, you can get a very good creep properties also. Now, the question comes in whether they show the corrosion resistance, high thermal or neutronic application, that is yet to be explored yet. Okay. Now, if I on the left side, this if you see on the left side of the diagram here, that temperature versus yield strength. If you look, one of the most dominating alloys, they started dropping their strength as you cross the 1000 degrees centigrade, that is close to 1200 K. But high entropy alloy, particularly refractory based BCC metallic alloy, they retain their strength up to 16 to 1800 K, that is 1400 degrees centigrade. They can be application. So if the temperature can be maintained up to 1400 degrees centigrade, the material will not be the requirement for the reactor temperature point of view. So I can go operate my temperature at 1000 degrees centigrade without compromising the safety of the reactor, and that could be the very good point of this. This idea is not a very original idea. Actually, Professor Ben Cantor from UK was coining this idea in 1970s. But he was not getting the good ideas. He was trying something that 30 elements, 40 elements, half the periodic table into the allying element, and he was not going to the success. However, the first success came by the Korean group with Huang and Yang, who have shown in 1996 that it is possible to put 5 elements and reduce the number of phases to 1 and 2. That was the first time the imagination of the material scientists caught the attention, and that is where the high entropy alloy were taken up and then are very seriously pursued after that. So in 2004-16, slowly some rules were made. Now we have some thumb rules to figure out which elements can give what. And that is what I'm going to tell you in the next slide. But before that, I just wanted to draw your attention why high entropy alloys are important. See, now you think of BCC, it has two Wyckoff positions, 0, 0, 0 and half, half, half. And if we have 5 elements into that, and you can think of that if they are completely random solution, then we have 5 C2 configuration possible, theoretically. That means each unit cell has its own composition and which will be repeated after 7 or 8 unit cell pass by. In the process, what happens? Each unit cell is having very large lattice distortion effect to match each other. Now, when you have such a high distortion effect, what you get is a very sluggish diffusion process. And if you have a very sluggish diffusion process, what happens? Now, that is where I wanted to show about what positron can do. See, when you have whenever irradiation takes place, the Frankel pair generates one interstitial atom and one vacancy. In conventional alloys, the vacancies they remain the same place. Interstitial diffuse very fast, and in the process, the remaining vacancies they create lot of problems, and that is the reason which modifies the structure of the component. So what we can do in turn? So if we have a high entropy alloy, because of the very distorted lattice, sluggish diffusion, neither interstitial nor vacancy can move, and there is a chance of recombination. So property will not be deteriorated as it deteriorates in the conventional alloys. Okay, so this will improve the properties, at least from a nuclear point of view, at least on the concept. We have to show this on the experimental basis. Now, the point is, in ordered structure, when you show it to irradiation, exposed to irradiation, they go under the disorder transformation. High entropy alloy is already disordered. That is where they gain the strength by increasing the disorder. So something which is already disordered, you cannot further disorder it. So that is why structural stability will be very high. Now, the third point comes in is that suppose we have a refractory metals. Refractory metals has a high melting point. If we have a high melting point, then the structure will be stable to the very high temperature. So we thought about all this point and we started looking for what are the possible elements. So if you in that right bottom, you can see the configuration of the high entropy alloys. What should be the structure? That is the difference between the atom size should fall between 0 to 8.5. Enthalpy of mixing should not be very high, otherwise you will end up with the intermetallics. Entropy should be as maximum as possible. So that's the way, if you start looking theoretically, then entire periodic table you can map which are the elements possible to get the high entropy alloys. For example, we know aluminium shows FCC structure. So if you add aluminium, will go in the high entropy alloys in the FCC based structure, but it's a lightweight element, very low density, close to 2 gram per cc. So titanium, aluminium, magnesium, lithium, beryllium, if I add, definitely I will get a very lightweight high entropy alloy, which is a FCC structure. You want SCP structure, look for element which have FCCP structure. Now in SCP structure, if you look down, you will find that the most of the elements are coming from the trans series of elements, gadolinium to holonium and yttrium and all. The idea is, if we have these alloys, very high structure, they can show very high magnetic property, very hard magnet they can make. So these are the many possibilities are there. Among them, if you look around in the middle of the table, which is showing that the blue color, sky blue color, you can see that zirconium, niobium, moly, your hafnium, tantalum, tungsten, vanadium, these are the BCC refractory metal alloys, and they show BCC metal alloy. This is our point of attention here. Now, from nuclear point of view, as I was telling before, my residual radioactivity should not be very long. So if I map the entire periodic table again in terms of what is the residual half-life of the elements, then you will find that these elements, vanadium, chromium, manganese, tantalum, tungsten at least, they show half-life as low as 50 years. Okay, we can go to 100 to 300 years. So we know which are the elements to add. So if I map these two colors of the periodic table, I can quickly find out which are the alloying elements we can go with to form the alloying elements to high entropy alloys. Keeping this in view, we started our study in DRC. So we divided it as usual in BRC. We try to work on the research and on the development. So left side is showing the basic study where we want to do the research. The idea is 20 zirconium, 20 niobium, 20 vanadium, 20 tungsten, and 20 equiatomic ratio, and you get the highest entropy of 1.5. Why we are doing it is zirconium and titanium, they form in the same group of element, group 4 element. Vanadium and niobium form group 5 elements. These all 4 elements shows the phase separation tendency. They have shown the segregation tendency, that if you put in the alloy system, they will at zirconium atom try to segregate, niobium try to segregate in another place. In contrast to that, aluminium shows the ordering tendency. So if we put all these things, there is a cocktail effect and we can get a very nice structure on that. And this is what I wanted to show right now. We will go a little later on that. And based on that, when we were doing this study, we found there is actually composition can be tweaked, and we can find that for there can be another compositions which can show single phase structure, and that structure is shown in the next series where you find that one of the phase in the study of the first lab when we did was we found this phase was showing the single phase, and that was 35 niobium, 20 vanadium, 25 titanium alloy systems. In addition, see, we were trying to explore for the superconductivity. Why superconductivity? See, superconductivity is basically that how you can quickly form the Cooper pair, which remain stable to the highest temperature. That gives the you very good superconductivity. Now, as I was telling you that each unit cell is having its own composition and they have lot of strain among themselves. So the Fermi surface will disintegrate because Fermi surface cannot maintain integrity across the different unit cells. So it will form a Fermi band, and because of the lot of room available at electrons may have chance to form the superconductivity. That is the idea of exploring this. And there are some other on the right side. If I show you, there is a high entropy alloy which can be proposed for the fusion or the that is I am talking about fission reactor. That fission means fast breeder reactor I am talking about, where neutron flux is more than 1 MeV energy, average energy. And we have worked out all these alloy and trying to show what is happening and what was our application. For example, the first alloy series we did by casting as well as by powder metallurgy route. The second series of alloy we have shown the single BCC phase which we could get directly after melting. See, in the entire high entropy alloy, the mother of the problem is to find the single phase alloy, and then you can work on that. So this is some of the preliminary work which I wanted to show here on the high entropy alloy. And let me take you to the next of that is what we did. We have done a lot of thermodynamic calculation, some simulation work, lot of calculation, and then started based on that we arrived to certain composition. Then we synthesize the alloys by vacuum arc melting, levitation melting, suction casting, or powder metallurgy route, and then do exhaustive characterization to figure out what is happening. And in this process, we did some of the work. For example, let me take you the first alloy, which I have shown you before. The first alloy, when it was made, see the thermodynamic calculation when were done, it shows that yes, it should, this all thermodynamic parameters predict that it could be a very nice high entropy alloy. So we started our work on that, and the alloy was melted and it was cast inside a crucible of copper cooled crucible so that high cooling rate can be prevailed. And what you can see, actually it does form a BCC structure. But apart from the BCC structure, it is also showing this is X-ray I am talking about. XRD, you can see two phases for there, and another is ordered BC structure, what we call it a B2 structure. So in this alloy, what we see that at the grain boundary, that the boundary which was touching the surface of the cold copper crucible did have a second very strong single grain material. But as the temperatures, as you go down, because the cooling rate has fallen down, the structure started decomposing in two phases. These two phases are the BCC and B2 structures. So when hardness was done, you can see their materials are really, really hard. To just put the thing in the right perspective, if I take the steel, my typical steel hardness is close to 300. So they are nearly twice as hard as the conventional steel material. That is, I'm talking about the high strength steel. When we did the TM and high analysis, there was a very minor phase. Second phase was very, very minor. But the primary phase was generally BCC structure, and the primary phase was showing, secondary phase was showing some SCP structure. And if you take the high resolution electron microscopy, I'm very sorry for slightly poor things. It is, so I'm not able to resolve here. But I can, atomic resolution, you don't see any ordering structure is there. Whatever little you see is because of the strain matrix, which is not allowing to give a very clean picture of that. So the phase what we have found is a single phase material. We had gone for that and started looking into the material. So this was on the left side is as cast material, but when you do the laser surface on that, the same single phase grain boundary can be increased. You see on the right top material on that. And then we did the levitation melting, and in the levitation melting, rolling was done, crystallization was done, and solutionization was done. And in the process, we end up with a single phase material by levitation melting, solutionizing, and then heating at 1000 degrees centigrade for 96 hours. So when you do that, you do form the single phase material. So this does show, but it's a sluggish process. So what one can do, but it also shows the structure is very, very stable. So in the phase what we found in the at the edge of the ingot, that phase, that composition and was it shows the material. There are two phases now. There are two, but they had a different composition. They change in the composition. So we started looking. Now I will just because time is running short, so I will just quickly go on the some of other small work on that. That is, we did some of the basic study on the hafnium based alloys. And what I wanted to show over here, you see the microstructure. There is a dull two-phase microstructure. I'm not able to get. This is the dull microstructure where you can see the dendrite structure and interdendritic region. And if you examine the composition along this line, what you see, there are phases have a tendency to segregate. There are certain elements which segregate on one phase. There is another element which segregate on another phase. However, the phase, though compositionally phase is showing two composition, the crystal, from crystal structure point of view, there is a single phase on that. And that is the point which is of very interest to all of us. So we started examining this phase little extra to find out what is happening, why it is happening. So when we did the DT analysis, we had gone up to close to 1400 degrees centigrade, back and forth several times, no phase transformation, no change, no formation on peak or no any enthalpy change. What you see, the BC structure is rock solid up to 1400 degrees centigrade. Then another issue was to test the same material under the high pressure. High pressure means I am starting and going to the 50 GPa close to, and what you see over here is that after crossing close to 45 DPa, the little bit formation of another phase form, but major structure, it remains BCC all along. So these are in situ XRD taken under changing pressure condition, and you can see that material does not show any degradation up to 50 GPa strength, not DPa. Sorry about that. Now, I just how much time I have left? Huh? 5 minutes. 5 minutes. Now, now the point is, now the same material we was taken for the hafnium, the same material taken for the superconductivity study. Now in the superconductivity study, why we have taken, I was just telling you, that in high entropy alloy, my Fermi surface is broken into Fermi band, and then you can see how uh, how these are occupied. And when we did the DOS calculation, that density of state calculation, it does show there is a region where it can have a very high tendency for superconductivity. And these are the curves which are shown experimentally. And you can see that as the temperature is brought down below 4K, it started showing superconductivity at various temperatures. Now the question is, 4K you may see is a very low temperature. What's so great about it? The point is that if I take individual elements and try to figure out their superconductivity is even is very close to this, but this shows very high magnetic very high HC value. That shows that cocktail effect does work. That once it forms superconductivity, it does not distort. It remains over there. And all the calculation done over the of the heat capacity and other calculation has shown this actually follows the entire BCS theory. That is, it shows the same tendency of the forming the Cooper pair by the phonon coupling, and it also shows that electronic specific heats takes the hump. And all these calculations show that your SC2 temperature, if you start looking, then it crosses more to 8K. Now, in a low temperature metallic system, which is not intermetallic, this is one of the highest SC2K which has been formed into any superconducting materials. Now, once we get excited about this, we started working on another alloy system. Why not to look for a material which can have an even higher tendency for the superconductivity? So we explored another material where instead of that we started adding copper on that. The moment you add copper, you are actually deviating from the high entropy alloy concepts, and what you end up is the formation of a single phase again, but composition is different. But in between, very faint, if these are the very small lift out, fib lift out, which show this is nearly 10 nanometer lift out, and you see these small patches, they show a phase which is showing some ordered structure into that. Okay, now I will quickly try to run some of the work I wanted to show on that. This is done on the your engineering side of the things, where high entropy alloys, how we have produced. We did detailed calified calculation and showed that conventionally, if you take the calified structure, we found out the composition of the alloy and then started looking into the material. See, if I do the ball milling, the composition shows a single phase, very small single identity of the single element like chromium and vanadium is present there. But as you do the further conventional centering of these phases, peaks go off. And when you do spark plasma centering, that is, you give the pulsating electric current while the centering, then the region gets welled and you get a very fine structure, and it shows the very fine plasma spark single phase material on that. And if I just take this study to further up, after melting, now we have identified some of the high entropy alloys, that is titanium, chromium, vanadium alloys, which is having a density of 4.9 gram per cc. Let me tell you, titanium has a tendency, density of 4.4. So we are very close to titanium based alloy. Single phase, it has a strength price of the titanium alloys, ductility as good as titanium, and this possibly can find an application in the aerospace application. My collaborator was not ready to share more than this because they feel that it has some potential for the application. So I had to move to the other alloy system now, and I am showing some for advanced reactors, some of the single phase material we have found, which have the low activation elements present on this, and they remain single phase all along the phases. And that is where I wanted to basically share some of the work, but that is how to use positron annihilation to figure out where the strain is there and where the defects are generated. So we have already done some irradiation experiments to generate a lot of irradiation induced defect, and that will come to positron lab for generating their curves to figure out how much we have that defect into the materials. Based on this, I will just quickly I have just scratched the surface. I just wanted to tell you that, see, why high entropy alloy is giving another spin to the story of material development is they have highly disordered structure. Once they have highly disordered structure, they find very good mechanical strength, very good corrosion resistance. We have done the corrosion study. They show very good corrosion resistance. Irradiation resistance is something which is still under the investigation, and many of may find some application, I suppose, in the future. And now we are working on the proxy ion irradiation, where we believe that positron annihilation spectroscopy is going to play a major role, because other conventional characterization technique do not basically do not separate the strain and the defect. Positron, I think, is the only technique which can do that. With this, I will end my talk and thank you for your kind attention.
Yeah, Dr. Tevari, thank you. This was a very interesting talk. I've learned quite a lot about this high entropy alloys. So development is going on, and we can expect improvement of the material properties in the future. I was just, let me see. Oh, there's a question of Andreas Wagner, but let me ask first my question. So we know that this material has very superior properties, so chemical resistivity. If you try to etch the sample, you will see it. It's not possible to etch them, so only with very special recipes. Then, of course, radiation hardness and so on. So it would be a very nice material, but the question that I have is where to get it. I mean, you have this arc melting, so you get milligrams or grams maybe. But if you want to have machines or say balls of fusion reactors and whatever, so you need more material. Do you see a way to produce them with more volume? What do you think?
Actually, some of the material which are for engineering applications, they are already being melted in a 10 kilogram
Okay.
steel. We have already done that. And chemical homogeneity was questioned at some time, but with the skull melting techniques, we can overcome that problem too. Currently, we up to 5 to 4 kg, we can successfully produce in the, of course, in the means in between lab and commercial stage. So we have already, in collaboration with the one in India, one unit, commercial unit called Medhani, and we are going to produce this material in a slightly larger quantity to test the possibility of structure application.
Okay, thank you. So there's a question of Andreas Wagner. Niobium-94 has a half-life of 20,000 years. It is favorable to have niobium as a component in this high entropy alloys. So to exchange this
No,
niobium-94 has a too long lifetime. Yeah.
I agree to that. That's a very good question. See, in the fusion reactor, we have avoided niobium. If you see, we have gone for tungsten and vanadium based alloys. Niobium alloys were basically explored because by adding niobium, you can retain some ductility into the material, which is generally not possible if you are adding too much tungsten and vanadium based alloys. So that is where some compromise was done, but we do have one alloy system where niobium is not there at all. That's, I think, one of the last one I've shown was not having the niobium.
Okay. So there's a chance to avoid this, simply to avoid this very high half-lives of isotopes. Yeah. Okay. So that's another question from Priya. What is so special about single phase? Why achieving single phase is important?
Single phase.
Yeah, that is the question. Why is it so important to have single phase material?
See that when you want, otherwise you will end up into the multi-phase, multi-component system. Multi-phase means the concept of high entropy is not strictly valid. See, to have the entire advantage of high entropy, you should have these all elements embedded in one single phase. That is why single phase is important. Otherwise, you will have multiple phases, each will have its own composition, and then they can form ordered or disordered, whatever kind of a structure, and your high entropy advantages are lost.
So you think it's really a good property of the material that it simply stays always in a single phase, yeah? So this
Should be.
is, yeah.
So nowadays they call compositionally complex alloy, CCA.
Okay.
That is where they have the multiple phases. Each phase is a high entropy or medium entropy alloy, but you will have multiple phases. So
Okay,
overall
okay.
configuration can be high entropy.
Okay, so I see no other questions. So then I would like to thank you once again.
Thank you. It's my pleasure.
Okay, so just to say for the others, we are still good in time. Then the talk of Dr. Tiwari was upgraded to an invited talk. So therefore we are just in time, no problem. So next speaker is Dr. Ranyal Mittal, also from BARC. Dr. Mittal is working on as scientific officer at Solid State Physics Division, Baba Atomic Research Center, Mumbai. He is interested in lattice dynamics, inelastic neutron scattering, neutron instrumentation. He was a recipient of Omar Baba Science and Technology Award in 2015. So title is Defects in Highly Neutron Irradiated Graphite. It seems to also be a very interesting talk. So Dr. Mittal, the floor is yours. Please, go ahead.
सर शेयर करना
I can start.
Yeah.
Thank you very much for the invitation. The title of my presentation is Defects in Highly Neutron Irradiated Graphite. As you know, we have Cyrus reactor, which is now closed. So from this Cyrus reactor, which was operating for about 40 years, we have used graphite samples to study defects in those highly irradiated samples. So this is my I am Dr. Ranjan Mittal, and for this work, these are the collaborators from Solid State Physics Division. H.K. Koswal, he was involved in Raman spectroscopy, and Babu was involved in specific heat measurement, and Rakesh Ranjan, he was involved in preparation of samples, and Ratikant Mishra, he did DSC measurement. In our group, basically, we are using lattice vibration for study of phase transition, thermal expansion, and elastic properties of samples. And we are studying the dynamics of atoms in solid. We are using both the experiments as well as computational techniques to study thermodynamic behavior of compounds. We are doing both the types of experiment using single crystals as well as using polycrystalline samples. And from whatever data we get from experiments, if all these data are analyzed using computation, we do lattice dynamical calculation based on empirical potential as well as ab initio calculation, and we also do molecular dynamics calculation using both the empirical as well as ab initio methods. Using these techniques, we study phase transition, anomalous thermal expansion, like some material contract on heating, diffusion in solids, crystal structure under steam conditions, phonon dispersion relation, equation of state, and thermodynamic behavior. During the last few years, during 15 to 21, we have understand the anomalous thermal expansion of various compounds like this, because these are the compounds which contract on heating, and we have explained the what is the reason for this underlying mechanism of anomalous thermal expansion in this compound. And we are studying the diffusion in battery material, Li2S, LiMPO4, lithium aluminum silicate. We have provided correlation between lithium diffusion and dynamical instability. We have studied nuclear compound YbO4, graphite, RePO4, and here we have studied thermodynamic properties and high pressure and temperature phase stability. And we have also studied multifluoric compounds. And here our purpose was to study role of phonon instabilities in leading to structural distortion and phase transition. So based on this, we have recently published this review article in Progress in Material Science. This is purely devoted to anomalous thermal suspension, this set of compound, and this is another review article based on my PhD work. And today my talk would be mainly focused on graphite, which the samples for which were obtained from Cyrus reactor. So now I start my main topic of my presentation: defects in highly neutron irradiated graphite. As we know, graphite is used as moderator or moderator or reflector in many reactors, especially research reactor, and about 250 kilotons of irradiated graphite inventory is present over all the world. This is the structure of the crystal structure of graphite. In plane, we have a strong covalent bonding, and between these two layers, we have a weak van der Waals bonding. So when this graphite is subjected to highly irradiation environment, then irradiation results in knocking off atoms from the from this equilibrium site, and this atom sits in between the layers. So, and when we heat this graphite, then this interstitial atom return to their original position at about 200 degrees centigrade, and this results in large release of energy, and which is called which is known as Wigner energy. So there is a high interest in understanding the change of in behavior of graphite as well as in other graphitic material such as graphene and carbon nanotube. What is the effect of irradiation on this material? So for this purpose, we have obtained samples from, as I told you, from Cyrus reactor, which is now closed. So this is one of the plug, and from this plug we have obtained 12 samples. This is the front end of the plug, and from you can see this 0 means here. This is the front end of plug. We have systematically investigated various samples, 12 samples at various distances, and this is the thermal. This is the this plot shows that this sample number 0, sample at 0 position, how much fast flux it has faced over the period of about 30 years. EP thermal flux and thermal neutron. Fast flux and thermal neutron, various samples total. So thermal neutron fluence means neutron per centimeter square per second into time. So this is the total neutron fluence seen by various graphite samples, and this is the distance from this front end of the plug. And using these, for these 12 samples, we have done X-ray and neutron diffraction measurement to study the changes in the lattice, and we did Raman scattering measurement. We also did DSC measurement, small angle scattering measurement, and structural and we also did ab initio calculation to understand the release of Wigner energy. So these are the plots for the X-ray and neutron diffraction. We can see that this peak as we go, this is shifting to lower Q with irradiation. F0 means the sample which has faced the maximum fluence. So this is shifting to lower Q, means this indicate increase in length, and these are the various diffraction pattern from neutron diffraction, and this data is plotted here. This is plotted as a function of the same data. A and C is plotted for thermal neutron fluence, EP thermal neutron fluence, fast neutron fluence, and sample number. We have given for maximum the sample which has seen maximum fluence, we have given 0. So this has seen maximum fluence, and this is minimum. This is fresh sample. So we can see that whenever there is a some critical EP thermal or fast neutron fluence, then only there is a change in the lattice parameter. So otherwise, for this 4 to 5, the samples which have seen low fluence, they have not undergone any change. But as soon as there is an increase of from some cutoff value, then there is a increase in C parameter, and this is due to because C lattice parameter is show large expansion, and age does not show any change and change, because this is due to the fact that because along C between two layers there is a van der Waals bonding, which is a weaker bonding. So weaker bonding along C, because of weaker bonding, there is an increase in C, and in the AB plane bonding is covalent, so it would not show very slight decrease, but it is not showing any the effect is very not very significant. So, and we also conclude from here that the samples which have seen very high neutron fluence of epithermal or fast neutrons are damage maximum. So you can see that first these 4-5 samples have not seen any does not show any change with the fluence. And this is the DSC curve, and we can see that as we heat after 200 degrees centigrade, all the this Wigner energy is released. So these are the for few samples I have shown here what is the total neutron fluence they have seen, and what is the onset of Wigner energy, peak temperature, and temperature, and this is the enthalpy release from each of the sample. So to understand this, we have the defect. We have performed neutron diffraction experiment. We have measured S of Q. Here I have shown S of Q for two samples, the samples which have seen maximum irradiation and fresh sample. And if we take Fourier transform of S of Q, then we get G of R. And we show that in the G of R spectra there is a extra peak. Extra peak at about 2.2 angstrom, and which is due to the we have shown that if we this data we have interpreted using ab initio calculation, and we can see that this is the interstitial atom, and in the fresh sample after irradiation, if we, these are the various distances. So if this one atom is knocked out from here and it goes here, and from after this is knocked out from here, then this distance is reduced to 2.06 and this is increased to 2.66. But in the fresh sample, these L and M are same, and these are equal to 2.44. So this this peak at this position is due to the this new bond of 2.1 angstrom. And this also we have shown from our ab initio calculation that this additional peak we are seeing at about 2.1 angstrom in a we have created one Frankel defect in ab initio calculation in a supercell of 4x4x1 and 4x4x2. And these are the Raman spectra for all these 12 graphite sample, and we see that there are two peaks, defect peak and graphite peak, and this as we increase the level of irradiation, this the intensity of this defect peak is increasing. So this is the maximum irradiated sample, and this is the fresh sample. So we can see that with defect, with increased influence, there is peak positions are more or less same, but intensity of defect peak and pure graphite peak is increasing, and there is also an increase of the width of the graphitic peak, and this increase in intensity of defect peak is due to the breakdown of the Raman selection rule, which give contribution from the total density of state in the Raman spectrum. To understand this additional intensity in the Raman spectra, we also calculated phonon spectra because when once atom is knocked out, then we can see that this atom is 4 coordinated and this is interstitial atom, and this atom is 2 coordinated. So each of this, so now we have structure with 2 coordinated, 3 coordinated and 4 coordinated. So for each of these 2, 3, 4 coordinated structure and this interstitial atom, there is a different density of state because interaction would be different. So, we can see that this increase in intensity at this around 800 centimeter is due to interstitial atom as well as 2 coordinated and 3 coordinated atom, and this increase in intensity of the defect peak is due to the 4 coordinated atom. And this is the specific heat, and we see that in the maximum irradiated sample there is a slight specific heat is higher at low temperature, and this is due to the increase in because when we irradiated then there is a softening of the mode, and this softening of the mode gives rise to increase in the specific heat at the low temperatures. To understand this phenomena, we have performed ab initio molecular dynamic simulation, and we have created one defect in a supercell of 4 by 4 by 4 by 4 by 1 cell, and we have we have plotted total energy as a function of time, and we see that at 300K it is total energy is almost flat, and at 1000K this for 1 Frankel defect, this energy is completely released at 5 picosecond, and with 2 defect this lattice is not fully annealed. But if we go to higher temperature, then this lattice with 2 Frankel defect is also fully annealed, and these calculations were performed using our Aganya supercomputing facilities at BARC, and all these results are already published recently in Physical Review B. So to understand further defect formation, we have plotted here time dependence of fractional coordinates of all the atoms, and we have this color black, green, and red correspond to all these atoms, and we show how this atom moves with time. And this is the initial structure, and we see that about 2 picosecond this black atom pushes to green atom, and this is the position here, and then after some time this green pushes to red, and then this comes here, and this finally this at higher at about 6 picosecond this we get perfect graphitic layer. But at 900K when we do simulation, then we find that lattice is not fully annealed, and we find that there is a 5 coordinated and 7 coordinated structures in the lattice. To understand these, these are the movies. So we can see that at this structure is maintained this would show 5 coordinated and 7 coordinated structure, and this would show fully 6 coordinated structure. This is showing 5 coordinated and 5 membering and 7 membering, and here we would get completely 6 member. This is problem. Why it is not getting?
Explain. Next slide, please. Go to next slide.
Okay, and but it and this is the movie with 2 Frankel defect, and we find that after 4 picosecond both these layers would have 6 member rings. Because of this. Yes. Now this has become fully 6. So these are the conclusions. The measurement shows that graphite samples which have been irradiated with very high neutron fluence of epithermal and fast neutrons are damaged significantly, while the thermal neutron fluence is not so well coordinated. We have observed signature of 2-coordinated, 3-coordinated, and 4-coordinate carbon topologies around the Frankel defect in both the diffraction and Raman experiments. The macroscopic understanding of annealing of defect on heating is achieved through ab initio molecular dynamic simulation. These involve cooperative movement of several cascading steps depending on the distance between the vacancy and interstitial positions. The experimental and theoretical work has provided valuable insight in the understanding of structural and dynamical behavior of defects in neutron irradiated graphite. The annihilation of defects defect and consequently release of usually large beginner energy. Thank you.
Yeah, thank you for this nice talk. You got these carbon rods very heavily irradiated, but I don't know what happens to carbon when you irradiate this by 10 to 20 neutrons. Is it highly activated? Was it difficult to prepare the samples?
All these samples were irradiated in our reactor for 30 years because flux was 10 to the power 13 and total fluence is 10 to the power 21.
Okay.
If I multiply flux with time after 30 years, so our reactor was operating for about 20 years. So if I multiply neutrons per centimeter square per second and time, so I get a total neutron fluence of 21, 10 to the power 21.
Okay, so these were quite valuable samples then, because they have such
all
a lot.
These samples are not very easy to get all these samples, and I am still doing a lot more of studies on all these samples. And in future, I like to do positron annihilation, investigate all these samples by positron annihilation technique also.
Yeah, it sounds very promising. You should do that. There's a question from Dr. Tuta. Neutron irradiation causes Wagner defects. Isn't it Wagner defects? I'm not sure. Wagner defects in graphite. Then how does lattice expansion is taking place due to irradiation?
Because whatever atom is knocked out, it sits in between the two layers. When this atom is sitting between two layers, because of weak van der Waals interaction, this spacing between two layers would increase slightly. I have seen here, na? I have shown here.
Yes.
Because of weak van der Waals interaction, these are two layers. When this atom is knocked out from here and it sits in between two layers, so because interaction between two layers is weak, so there is a slight increase in C lattice parameter.
Yes. Okay, do we have more questions? You can simply raise your hand, I think. So seems not the case. So I would like to thank you once again for your very nice talk. Thank you very much. Okay, let's go to the next talk. Again, it's a short presentation from BARC, from Dr. Jyoti Prakash. He's working as a scientific officer in the materials group, Baba Atomic Research Institute, Mumbai. He is interested in the study of carbon-based materials for sensing and energy storage, photoelectric chemical water splitting, chemical coding, and interaction behavior in multi-hybrid systems. He received a prize. So title is Defect Analysis in Sodium and Potassium Doped BIVO4 Photocatalyst Systems for Photoelectric Chemical Water Splitting Performance. So, Dr. Prakash, the floor is yours. Go ahead, please.
Thank you, session chairman. And first of all, I would like to thank you, organizer, for giving me opportunity to present my work in this e-conference. So today I will be presenting on the defect analysis in bismuth vanadate system, especially doping with the alkali metals like sodium and potassium for water splitting towards the generation of hydrogen. So I will start my presentation with the introduction about the photoelectrochemical cell. Since this audience is new about the PC, I will just introduce a little bit about that. So this is a simple schematic of a photoelectrochemical cell where we use two electrode method. We have one photocatalyst coated electrode, and corresponding to that we have a counter electrode which is connected to a power supply unit. Now in this, when we immerse these two electrodes inside the water, and when the light falls over this photo, in this case I'm showing photoanode. When the light falls over the photoanode, the charge pairs are generated, and under the suitable applied potential, they reach to their respective electrode. Like in this, the holes reach to the surface of photoanode and they do the oxidation of water to generate the oxygen, whereas the electron reach to the counter electrode and they do the reduction of H plus ion to the hydrogen. This is the simple schematic of whole PEC cell. These are the experimental setup which we use in our lab. So we have a solar simulator which we use for generating one solar sunlight, and this is the cell where we put our water electrolyte based system, where we put 3 electrodes and do our analysis of different electrodes. These are the fabricated electrodes. Like this we fabricate them. Now this is the laboratory setup. How do we do the testing of our photocatalyst? Now the question arises whether using this kind of photoelectrochemical cell, we can generate hydrogen in the large scale. So just in a schematic I have shown here, yes, it is possible to generate hydrogen using this kind of cell. So for that, we have proposed a tandem cell where we have a photocatalyst coated on the one side. Other side, we have a counter electrode and connected to a PV cell. So this will be a standalone chip which if we put inside directly in the water, we don't need to give any bias potential through the external source. And when we irradiate it under the light, it disintegrate or split the water and generate the hydrogen. And there are different mechanisms we can separate the hydrogen, and we can generate it in a large scale. Like in the present system, in our calculation, we have shown that if we can achieve solar to hydrogen efficiency up to 10%, we can generate hydrogen in the price of less than $4 per gasoline, GGE gasoline gallon equivalent. So this is a very promising technique, and using only renewable energy, we can generate hydrogen in this case. Now the important part in this is the photocatalyst. The total efficiency of the system depends upon what kind of photocatalyst we are using. So what we are looking in a photocatalyst, it should have a good light absorption efficiency, especially in the visible region. It should have a very high chemical stability if we are talking about long-term hydrogen generation. And it should have a suitable band edge position towards the hydrogen reduction potential and the water oxidation potential for the efficient charge transfer. Now, if you look into the literature to the available materials, if you look into the literature towards the available materials, in the N-type semiconductor, bismuth vanadate is the one of the most suitable material which has a very suitable band gap and band edge position. If you can see, the conduction band position is near to the hydrogen reduction potential. So with this, we can get a very efficient water splitting for the hydrogen generation. That's why we have chosen bismuth vanadate in our study and carried out several water splitting. So if we take pristine bismuth vanadate as a system and do the water splitting, it shows very poor behavior. There are two reasons for that. One is it has a little wider band gap, 2.5 electron volt. That limits its absorption. So that we can overcome by increasing the thickness of our photocatalyst film. But there comes the second part, that it has a huge electron hole recombination. And in a typical bismuth vanadate system, when the light falls and charge pair generates, electron moves only 10 nanometer, whereas the holes are able to move only up to 100 nanometer. So if we keep the thickness of film less than 100 nanometer, then only we can efficiently separate them. But if we keep the thickness less, in that case, we will lose the absorption efficiency. We cannot utilize the whole light which is falling on the surface. So what are the strategies we can adopt to improve the performance of this bismuth vanadate system? So I have shown it schematically using a periodic table. We have a primary constituent, bismuth vanadate. Now in this we can do the doping using different atoms, whether we can do it doping on the lattice position of bismuth, vanadium, or into the interstitial position. Different elements have been tried and we have also reported in our lab. So with the doping, we can do the band gap tuning as well as we can enhance the bulk charge carrier separation. Second strategy we can adopt is we can put the metal oxide or metal sulfide based heterojunction on the back and forth of the bismuth vanadate. Even the thickness, if the thickness of bismuth vanadate is less, by putting this heterojunction, we can improve the surface charge transfer. And whatever charges are reaching to the surface, they efficiently do water oxidation. For that, we can use several co-catalysts or plasmonic catalysts in that case. So in today's presentation, I will be only talking about the doping part, especially sodium and potassium alkali metal. So starting with my work, so this is the typical electrode coated with the bismuth vanadate, and this is the surface morphology. So we can see that the surface is porous and it has a very good wettability also. And with the doping, the surface morphology doesn't change. Now, if you see the water splitting behavior that we correlate corresponding to the photocurrent density, we measure in 3 electrode setup. So if you see the bismuth vanadate, which is shown in the black, it has a very low PCD, that is photocurrent density. That means its water splitting performance is very poor. Now, as soon as we dope it with the our potassium or sodium, it enhances. For the sodium, it is high, and then as soon as we put the surface co-catalyst, it further increases. And so what are the factors which is playing a role for enhancement of this water splitting behavior in doped bismuth vanadate system? For that, if we see our PCD equation, so the PCD is equal to theoretical current density multiplied by the light absorption efficiency, charge separation efficiency, and the charge transfer efficiency. Now, these individual efficiency play a key role in the water splitting behavior of the bismuth vanadate system. So we have systematically analyzed all these 3 efficiencies. So first is the absorption efficiency. We have used UV visible spectrometer to analyze the absorption of this doped and undoped bismuth vanadate system, and you can see this calculated absorption efficiency. So with the doping, it increases, especially with the sodium doping, it increases most. And there might be 2 reasons for that. One, with the doping, whether the spectral region is increasing, the absorption spectral region is increasing. With the absorption spectrum, we see that the absorption spectral region is not increasing. Further, we have confirmed in later experiment. And if we see the band gap, which is calculated using the top plot, band gap is decreasing. These are the experimental results. That means the improvement in absorption what we are seeing, that might be due to the reduction in the band gap. Then next comes our charge separation and charge transport efficiency. So we have used these 2 equations to calculate the charge separation and charge transfer efficiency. So as we can see in the first plot, that is the charge separation efficiency. With the doping of sodium atom in the bismuth vanadate, the charge separation efficiency reaches to around 90%. That means in the case of sodium doped, most of the charge pairs which are generated when the light illuminates it are able to get separated. But the charge transfer efficiency is still, it is not very high. It reached up to 30% from around 2% or somewhere. So it improves, but it is still not very high, so that we can get very high ECD in that case. So I just listed all the data in this table. So you can see that the charge separation efficiency is reaching up to the max, which is 100%. That means near to the 100%. That means whatever charge pairs are generated, they are able to get separated. Now transfer efficiency we have reached up to 33%, and absorption efficiency we have reached up to 73%. And if we see the overall efficiency, we have reached up to 22.6%. So if we compare with respect to bismuth vanadate, it is quite significant. And further, using this our efficiency equations, we have calculated IPC, that is incident photon to current efficiency. That means whatever photons are light photons are falling on the electrode surface, whether how much percentage of that is being converted for the water splitting. So with the sodium doping, we can see that we can reach up to around 40%. So around 40% of the light which is falling on the surface, we can use for the water splitting purpose. So that means doping is doing a positive effect, especially with the sodium doping. Now further, how this behavior is correlated with the crystal structure of this doped bismuth vanadate, that has been analyzed using the XRD technique. So in the XRD, we did the ritual refinement also. With that, we have seen that there is a slightly increase in the unit cell volume. So that suggests that the dopant, what we are putting in the bismuth vanadate system, it might be going to the interstitial positions. And further, with the Raman spectra also, it confirms that the increase in wave number towards higher, that shows that our bonds are weakening. Then further XPS data we have used to analyze it. So in this, the bond energy for the bismuth and vanadium is decreasing. That so again shows that when our dopants are going to the interstitial positions, they are exerting some electrostatic repulsive forces. Due to that, our bismuth oxygen bond and vanadium oxygen bond energy is increasing, and because of that, the bond might be increasing. That's the reason for the increase in the unit cell volume. And further, with this oxygen peak, XPS peak, you can see the maximum interaction we can see in the case of sodium. So sodium has most effect in the crystal lattice. So now we know that we have a bismuth vanadate system in which our dopants are going in the interstitial position. Now how it affects our like band gap properties or absorption properties. For that we have done this DFT simulation. For that we have taken the unit cell of bismuth vanadate and we have placed sodium at different position. I am showing the only the lowest formation energy scheme. We have put sodium in the different lattice position and we calculated its formation energy, and we have taken based on the lowest formation energy. So in that we see that with the doping of sodium, the space group of bismuth vanadate is not changing. And if we simulate its a band diagram, we saw that there are 3 interbands formation that I have named as a interband 104, 105 and 106. If we see in these interbands, what are the elements responsible for these interbands, we clearly see that due to the doping of sodium into the interstitial positions, they exert some kind of, they form some binding with the oxygen. Either they are sharing electrons or they are with the bonding with the bismuth or vanadium. So due to that, we see these 3 interbands. Now, when we simulate this band structure towards the absorption curve, the last one I'm talking about. So in this, we see a extra P. That shows that our enhancement in the absorption might be due to formation of these interbands, which further helps in improvement in absorption. And with this, the calculated band gap also shows that there is a reduction in band gap. So due to formation of these interbands and reduction in band gap is the reason for extra absorption, what we are seeing in our experimental results. Then further we have analyzed the bulk defects using the depth dependent Doppler broadening spectroscopy. So in this, basically S parameter is analyzed with respect to the positron implantation energy and the positron diffusion length for different samples is calculated. So we can clearly see for bismuth vanadate, the positron diffusion length is around 9.6 nanometer, whereas it is most for sodium doped bismuth vanadate, that is around 54 nanometer. That shows that with the doping of sodium, the defects are decreasing in the case of sodium doped bismuth vanadate system, and that gives a positive like result for the water splitting. That's why we see the enhancement in photocurrent density during the water splitting reaction. Next, we have again analyzed the surface defects also. This is mostly on the bulk side. We have analyzed the surface defects using the electrochemical technique. In that, we measured the CV in a broad range. Now, in the CV, we have a two reason. The first reason is reversible. That reversible reaction corresponds to the change of vanadium +4 to +5 that we have shown graphically in the left hand part. So that doesn't act as a recombination site. Whatever electrons are get trapped in that state, they get released also. But when we see the next part, second reason, there is a top. In this top corresponds to this reaction of BO2 plus, which is available on the surface in the presence of our aqueous solution. It acts as a recombination site, and when the electron goes there, it gets trapped. So in the left hand side picture also I have shown the electrons, when they go to these recombination sites or trap sites, they get trapped, so they will not be further available for our water splitting reaction. So this is the surface defect analysis with this also. So with this I will conclude the presentation. So by defect analysis, characterization and DFT simulation, we confirm that especially for the sodium doped bismuth vanadate system, due to formation, we see the improved PEC performance for water splitting and hydrogen generation due to formation of multiple interbands. There is a slight reduction in the band gap, increase in electron hole diffusion length. That means we reach up to maximum 91% around the bulk charge separation efficiency and high charge transfer rate. This I will like. Thank you.
Yeah, thank you very much, Dr. Prakash. That was a really interesting talk. Is there Mukhya, you have a question? Okay.
Yes.
Yeah, okay. Until I see the question, maybe I can ask something. So it's obvious nowadays, for me at least, that hydrogen is a new fuel, and in the future, say, I don't know what's the time scale, but I think we missed to promote this technology everywhere in the world. But now, okay, you can get the first cars and so on. Actually, here in Halle, we have a fuel station giving you also hydrogen. But this is one of 50, I think, in Germany only. So we are far away from the point that this will be a technology for the future. But I think it will come. What is your impression, especially in India? Is there a strong tendency to replace other fuel technologies by hydrogen, or is it just your research is very separated? What do you think?
Yeah, still in India, it is in the research stage. Like especially hydrogen stations and all those are still far away. Still we are in a mode where we are generating hydrogen in the large scale using different techniques like water electrolysis method. So the biggest challenge in India is storage. Generation we can do using different present available systems with different high energy consuming techniques, but storage is again a challenge here. So we see not very near future, but surely in the future we will be also adopting this hydrogen technology.
Okay.
And
Yeah.
especially what I'm talking about, this is based on the renewable energy techniques. So
Yes.
even in the US also, DOE and RREL are targeting it as a future technologies. They have not still adopted this in the commercial scale. The technology still has to be proven on the commercial level. So
Yeah, I
we are
see.
looking forward for the future of hydrogen.
Yeah, I think although you can buy cars here which are hydrogen driven, but this is also not. This is the very beginning. It's the very beginning. But I think
Yeah.
this will be really the future. So this is because if you burn something without any damage, then you have to burn hydrogen. So nothing else, nothing happens then. So this is you have no carbon dioxide. You have no other. Bad things that you can expect. So this is the future. I'm sure about this, and therefore your research is also the future. So congratulations for your results. So let me check. Oh, there is actually now a question. The question is, in your conceptual design of high throughput cells, can you please explain how it works? Does it require any power supply connection? Did you catch the question?
So yeah, we need a bias potential for that, definitely. So if you look, you can show it. So basically in that a PV cell is connected. Okay.
So I think they upload your talk again.
So basically we have a photo anode that is connected to a cathode. In the back of cathode, we have connected a PV cell. That's a PV cell that will provide the our required potential.
But I think you can just explain it. It's okay. I think we will understand. Just explain it.
Again, that PV cell, when the light falls over that chip, that PV cell generates the required potential in that case, which is sufficient for doing this water splitting using these two electrons. That's the total methodology adopted in that. So in that case, we don't need to use any external power source. Under the illumination of light itself, the PV module also works in that case, and that gives our required potential, and those two electrodes work as a PC.
I think this was a clear answer. Thank you. So I think time is over and we have to come to the next talk. I would like to thank you once again.
Thank you.
Thank you. So next talk is an invited talk from Marie-France Barthé.
Huh?
Okay, so and Dr. Barthé is working as a senior researcher in the laboratory, CEMHDI, whatever it is, at the University of Orléans in France. Her research activities include the study of defects in materials using positron annihilation technology, spectroscopy in combination with various other characterization techniques. And Dr. Barthé, Professor Barthé, will organize next Lopos in 2 years from now. And so we all know her very well. And Marie-France, the floor is yours. You have an invited talk, so it means 30 minutes, please.
Thank you very much, Renat, for this kind introduction. I would like to say good morning, good afternoon, and also good evening to all the people who are listening now. I am very happy to would have preferred to be in Mumbai with you. I would like to thank the organizers for this workshop. Very good job. And I think it was very important to keep in contact. And we had a very good week with very interesting and inspiring presentations. Unfortunately, without late discussions in front of a beer glass, but at least we were together in each other in our box on the screen. I would like also to thank the organizers of this meeting for their invitation and giving me the opportunity to show some of our recent results on positron studies in self-irradiated tungsten.
Marie, you should share your talk with us.
Yes, I will. Thank
Okay.
you.
Okay.
If I have the right to do, because I do not, it is not possible because my seems that okay.
Now it should work.
It's okay. Okay. Thank you. So, do you see my slide?
Yes, perfect. Thank you.
Okay. So, sorry, my pointer. Everything's studies in self-irradiated tungsten have started several years ago, and with the support of Eurofusion project and also for the French Federation for Fusion. And before to show you our results, I would like to summarize very briefly some elements of the context and our motivations. I will just say a few words because Mrs. Maya explained yesterday's challenges of the fusion technology. So I just will give you some elements. Just to recall you that this fusion could be a new challenge for energy production, and it is based on fusion between isotope of hydrogen. That's this reaction give helium and neutron and a high amount of energy. This fusion reaction has been produced on the Earth in tokamak, which are the first concept has been appeared in 50s, in years 50s. And in this tokamak, this gas, hydrogen isotope gas, is confined by a magnetic field to create a plasma at very high energy, and it allows the fusion reaction. There is now 50 operating tokamaks in the world, and we are on the road toward the fusion power plants. And on this road, there are few steps. The ITER tokamak, who is building in France, and the next generation, we call a demo, that should be a demonstration for the production of energy from fusion. So in this tokamak, the materials will have to withstand very hard conditions. Of course, high flux of hydrogen and helium, and also high heat fluxes with temperatures that could reach 700 degrees C, and also neutron irradiation. This irradiation could lead to elastic collisions producing pKas, that means per atom or recall atom, and it goes to the formation of a displacement, so vacancies, interstitials, and there is also some nuclear reactions which are created in the material. So there is of course, this irradiation will change the chemical composition and also the microstructure of material. And Professor Amarendra had a good talk where he summarized all the consequences of this modification on the material properties. So there is a big challenges in fusion technology for the materials to check that their thermal, electrical, and mechanical properties will be enough good for the operation. And one of material which is today very studied, we had several talks in this workshop, is tungsten, That's the metal which has been chosen to cover the divertor in ITER tokamak. This divertor is a key component. It allows to evacuate the helium arches. And tungsten is also candidate for the first walls in demo. So the damage induced by neutron radiation has been calculated in a CCFA, for example, and they show that the damage which will be created will depend on the position of the material in the tokamak, on the wall or the divertor. And for example, it can reach 12 GPa in 3 years in tungsten. We can see on the right here the pKa energy distribution. Of course, the tungsten is the predominant recoil in tungsten, and the pKa distribution is large and can go up to 1 MeV with a mean value of about 150 keV. So damage has also been studied by using TEM and in tungsten, which have been irradiated in different neutron reactors, that means fission reactors. And Asekawa and his co-authors show that loops and voids can be created, and the fraction of voids and loops depends on the damage dose in the dPa here and also the irradiation temperature. There is also some old results where the swelling of tungsten have been demonstrated in the temperature range between 600 and 900 degrees C. But the question is how we can project these results towards the future tokamak, where the neutron spectrum will not be the same as the ones in fission reactors. And to answer to this question, with one of the approach is to combine multi-scale modeling with experiments to be able to understand how the material microstructure change as a function of the irradiation and temperature. And our motivation is related to this approach and to make experiments to obtain some quantitative data on the generated defects induced by irradiation, and we use ion irradiations to make these studies. So first, there are a lot of studies which are dedicated to the dislocation loops, the observation of these defects in self-irradiated tungsten. And it has been shown that 2 types of loops are created, and their density could reach 10 to the 22 per meter cube in 0.4 dPa at the radiation temperature of 500 degrees C. And also there is a preferential formation of the 100 loops at low dPa. It has been demonstrated that the density and size depend on the temperature, and also that the size is a power law of, as it has been calculated using molecular dynamics. But there is less data on vacancy defects and cavities, so we perform TEM and PAS to add some data on this type of defects. So we will, during this talk, I will show you some results about the damage created and vacancy defects, of course, the effect, we will see the effect of damage dose, of temperature, and also the role of impurities. First, the virgin sample, that means the sample before irradiation. You can see here some Doppler broadening measurements as a function of positron energy. And you can see that this data can be fitted with effective diffusion length for positrons of about 100 nanometer. We measure the lifetime in this virgin sample and obtain something about 105 picoseconds, which correspond to the theoretical value for the lattice, for the annihilation of positron in lattice. And we obtain the annihilation characteristics, that means S and W in the lattice, which are here. So in the first study, we implant tungsten using helium-3 at 800 keV, different fluencies from 10 to the 14 to 5, 10 to 16 square centimeter. And we have seen that S and W value are aligned on the same straight line. We measure the lifetime for the sample irradiated at the highest fluence. We obtain 200 picoseconds, which is the lifetime which is expected from theoretical calculations, DFT. And we anneal this sample, and you can see here the low momentum fraction S as a function of annealing temperature. You can see there is an increase in S, and if we go to the S as a function of W here, we can see that when S increase, W decrease, and we have an increase of the slope. So we create some vacancy clusters, and these clusters are formation is due to the migration of the single vacancy, which appear in this 500K, around 500K temperature. And we also measure the lifetime at this annealing temperature, and we found two components with the longest at 460 picoseconds, which corresponds to vacancy clusters with a number of vacancy in or larger than 30, if we compare to the theoretical values. So now, if we go to the new results, the self-irradiation damage, we use different irradiation conditions. That means always tungsten ions with energy from 1.2 to and 20 MeV. And you can see here the stream calculations of the damage profile. Of course, when the energy is low, the damage region is very close to the surface, here in 50 nanometer, close to the surface. If we increase to 2 MeV, it goes to approximately 200 or 150 nanometer. And for 20 MeV, the maximum of damage is reached at about 1.34 micron. And it is interesting to see that in this region, we have not too much change in the DPA level. And this region corresponds to the region that can be probed by slow positrons. So the first 700 nanometer. So we are able to perform TEM observations and PAS in this thin sample or thick samples, and also in these thick samples. Okay, so just to remember that slow positron, we do the slow positron in SMT, and as I said, it allows to probe the first 700 nanometer under the surface in tungsten as a function of depth and we measure the low momentum annihilation fraction S and the high momentum annihilation fraction W as a function of the energy of the slow positrons. So if we look at first the results at low dPa and low temperatures, irradiation have been performed at room temperature and with 0.02 dPa. Here you see some TEM images in over focus and under focus, and you can see this black point and white point, which corresponds to cavities. That's the first time that cavities are observed in such irradiation conditions. And we have been able to measure the size distribution of these cavities. And we can see that these cavities have size from 0.5 to 0.8, we could say. And this distribution is not symmetrical. And because the detection limit of TEM, which is about 0.5 nanometer, we don't see what happens, of course, in this lower size part. So if we compare this distribution with molecular dynamics calculations of cascades in tungsten, you can see that this distribution starts from a single vacancy to different vacancy clusters. And if we draw this kind of distribution on our experimental one, we can, of course, we should expect some smaller vacancy clusters. And of course, these smaller are not visible with TEM. So we have used positrons and measure the S as a function of the energy in a same type of irradiation sample, irradiated sample. And we can see here that the SW point is very close to the one for the single vacancy. So we can say that majority of single vacancy are detected in this sample, and also some small clusters because we are a little bit higher above this point. So so we see as in TEM the vacancy clusters and also of course single vacancy with positrons. So now, if we look at what happens when we increase the dPa level, this time the sample have been irradiated with 2 MeV tungsten and at different frequencies corresponding to a dPa level from 0.085 to 1.7 dPa, and we can see that S increase with the dPa level and W decrease, and we fit this data using VecFit, and we obtain 2 different damage layers. The first one, which is where we can find the highest S, corresponds to a depth of about 100 to 150 nanometer, as it was for the swing depth profiles. And we extract from this fit the different data corresponding to the S and W in the layers, the ratio, S layer minus SL, so and W under W layer on minus WL, and also the diffusion length, the effective diffusion length. We can see that S increases and W decreases in this first layer. The effective diffusion decreases with that means the density of traps increase, and the slope also increases with dPa. You can see here from 0.96 to 2.15, indicating that vacancy clusters fraction increases. And you can see also that from 0.85 dPa, the S, W, and also the diffusion length remain constant, and also this slope. Okay, so it has been possible to extract the concentration of vacancy defects for the lowest flow dPa level, and from the effective diffusion length using this equation, we obtain a concentration or very high concentration of 10 to the 25 per cube centimeter using this different data. And for the higher damage level, it is not possible to really extract the concentration because this effective diffusion length is very short, but we could say that it is higher than 10 to the 27 per cube centimeter. If we now compare the data obtained at 2 MeV with other conditions, 1.2 MeV at 0.02 dPa and also 20 MeV at 1 dPa and also 13 dPa, we can see that there is no change of the S value as it has been observed for the 2.2 MeV tungsten. And so it seems that there is a saturation. And the question is it a saturation of positron signal or of the damage distribution? And if we compare this data with some calculation, using the creation relaxation algorithm, it corresponds to Frankel pair accumulation in the boxes, and look at what type of defects still exist after different damage dose. And we can see that there is also saturation in this calculation with a concentration of vacancy that is about 2 or 5%, depending on the empirical potential which is used in this calculation. And it is close to the number that we obtain with positrons. We also check if this positron signal saturation exists by annealing the samples irradiated at different dPa level. And you can see that from 0.03 dPa to 12 dPa, there is exactly the same behavior of the S as a function of annealing temperature. And there is 3 annealing stages. The first between room temperature and 600 degrees C, where we can see the formation of large vacancy clusters. And after that, we have a stage between 600 and 850, where nothing happened. And then the S decrease corresponding to the damage recovery. So we can see that for low dPa, that means 0.03 and 0.06, the size of vacancy clusters increase here. And for the high dPa, that means 1 and 12, there is no difference in this behavior. So we can say that defects distribution was equivalent for the dPa when the dPa level is higher or equal to 1 dPa. So it confirms that there is a saturation of defects distribution when we reach so high dPa. And there is something interesting, is also this point, S max W min, and we will ask if it is a new annihilation state. So we have this saturation of damage distribution, and we think that it is due to point defect recombination and also to the cascade overlapping, which induce vacancy cluster shrinkage, as it has been shown yesterday, if I remember correctly, by Farida, in iron, where the vacancy clusters, which is created first cascade, it can be shrink by the interstitials that are created by the second cascade. So we have this damage threshold of 0.5 dPa. And I will come back to this question, what is the S-max W mean? If you remember, I showed you some annealing for the helium irradiated sample we found at the temperature of 873 K. We found two lifetimes with ones corresponding to vacancy clusters, and the second one at 180, not too far. And the question is, what is this lifetime? To which type of defect it corresponds? We can say that this point, so corresponding to these annealing conditions, is on a line between 2 points, the S-max and W mean, and this star that could be this lifetime. This star has been plotted using the intensity of these two this lifetime decomposition, and we obtain the values of S and W for this defect T, with a slope of this magenta line corresponding to annihilation competition between this state and T1, which is of 3.66. And we think that this point corresponds to annihilation in vacancy clusters, large vacancy clusters, with n number of vacancy larger than 30. So now we can ask what is the role of purity of tungsten material on the damage which is created by irradiation. And there is several sources of impurities that could be, of course, the plasma. That means hydrogen and helium, and as shown that it leads to the formation of bubbles or fuse. There is also transmutation elements from tungsten, which produce rhenium, osmium, and tantalum, and it has been shown that it creates some precipitates in the material. And there is also some light elements, such as carbon, nitrogen, oxygen, which comes from the reactor environment, and also that are impurities in the material, virgin material. And it has been shown that various impurity defects complexes can be created. Here you can see some results of OKNC simulations with a different concentration of carbon, and the formation, that means loops, density, and the size of these loops as a function of damage dose, and increasing the concentration of carbon. So there is some high interaction between carbon and loops. Concerning the vacancy, there is also some interaction which are expected from DFT calculations. The binding energy between these different type of light elements is higher than 1.2 EV, and can reach 3 EV for oxygen, for example. And it can be also possible to trap several of these atoms in the same single vacancy, for example, here for the carbon in a single vacancy. Then, so we decided to study what will be the effect of the purity on vacancy defect distribution. We irradiate two types of sample. That means ultra high pure at 6N, and also high pure 3N, different tungsten, polycrystalline tungsten, using 20 MeV ions with fluence corresponding to a damage dose of 0.02 dPa at the maximum, and the temperature which has changed from room temperature, to room temperature to 500 and 700 degrees C. And you can see here the S as a function of the energy for the virgin, the sample irradiated at room temperature, and the ones irradiated at 500 and 700. And we can see that for the same, there is a clear difference between the two purities, and there is the highest S for the highest pure sample, and from the fit, using that fit of this data, we obtain the points which are on this graph on the right in violet and red. The red for the highest temperature and violet for the lowest, 500 degrees C, and the open symbol for the highest pure sample and full symbol for the lowest pure. So we can see that there is some vacancy clusters which are detected by positrons. And then we also perform a TEM on this sample, and you can see some typical images for the both purities for irradiation conditions at 500 degrees C. With the cavities distribution that has been plotted here for the different type of sample in range the 3N and in green the 6N at both temperature, and it is clear that the vacancy clusters or cavities are larger in the 6N sample. Here you can find the mean diameter and the density, which is 10 to the 24 per cube meter, sorry. And if we compare to what we could, to which type of lifetime it should correspond in positrons, we know that the vacancy clusters with a diameter larger than 1 nanometer corresponds to vacancy clusters with at least 40 vacancy in, and we know that there is this saturation of the lifetime for such large vacancy clusters. So, as for TAS, TEM showed that larger cavities are correct for the 6N compared to the 3N. And if we look at now this this data on this plot, the positron data, we can see that these points are aligned on a straight line going from the S max W min, which is the point corresponding to large vacancy clusters, and going to somewhere on the L1 line, which corresponds to annihilation in a single vacancy. So this magenta line has a slope of about 3.5, very close to the ones that we already obtained in helium implanted samples, and could correspond to annihilation competition with a T trap we saw just before. And if we go to the fit, we can see the effective diffusion length, which is about 14 nanometer in this sample irradiated at 500 and 700 degrees C. That could correspond to a total trapping rate, high total trapping rate. And if we assume that we have annihilation into two types of defects, that means cavities and T-trap, we can evaluate the trapping rate in the T traps, and it is about 5 10 to the 11. That corresponds to the concentration of the 7 10 to the 25 per cube centimeter. So what is the nature of this T trap? And we come back to the past for in this study from Rhiannon and co-workers in carbon-doped iron, where they demonstrated that the formation of vacancy carbon complexes lead to the to prevent the agglomeration of vacancy clusters. So we think that
Marie, excuse me, please.
I finish.
Yeah, okay, okay. You please finish in the next 5 minutes.
It is
Yeah,
my last. It is my last.
Okay, okay.
Sorry.
Thank you.
So we think that we observe the same thing in same kind of phenomenon in tungsten. And if we come back to the properties of the different light elements in tungsten, and we calculate the dissociation energy for this complex VX, we can see that at 500 degrees C, the hydrogen cannot be considered because this dissociation energy is too low. But all these complex with carbon, nitrogen, oxygen could still exist at 500 degrees C. So I just will summarize my talk and just saying that, of course, TEM and PAS are complementary techniques to characterize vacancy defects from single to clusters with more adapted technique for single and small size complexes detection for positrons. And we have seen that self-damage is created in tungsten with small vacancy clusters at room temperature, and the majority of single vacancies, which are only detected with PAS. We have seen that damage, there is damage saturation when damage dose increase above 0.5 dPa, as it has been expected from modeling, due to point defect recombination and cascade overlapping. And in irradiation at 500 degrees C, we have seen that in two different purities, we have seen cavities distribution depend on the tungsten purity. And we think that we found a new trap which should correspond to the complex between single vacancy and the impurities such as carbon, oxygen, and nitrogen. And I will thank you, my collaborators, and of course, you for your kind attention. Just remind you, Slopos 16 in France in 2023.
Okay, thank you, Marie. France. It was a nice talk, a bit long, but anyway. So we have no. We have a question from Professor Amarendra.
Yeah.
Let me try to find it. Oh, it's here. So for 2 MeV self-ion irradiation tungsten, have you observed vacancy defects from positron beam measurements at deeper depths than calculated by stream code?
Yes.
Did you understand the question?
Yes.
Okay.
I understand. I come back to the yeah, here. So it is not so. I mean, these fit are performed using a model with two layers, two damage layers, and two homogeneous damage layers. If we look at this depth profile, it is not made of two homogeneous layers. There is something which could look like a Gaussian, but it is not a Gaussian. So it is a simplified way to see this, and that means this thickness of the second layer could be lower, could be, yes, lower, and yes, it could be higher. So it is, to our mind, it is we simplified in fact this damage profiles. It's why we have this thickness of the second layer, which is larger than what is expected with swim. And of course, we have also to think about the swim calculation, which are not so exact. I mean, it is a way to an idea of this profile, but it is not so sure that it stopped at 300 nanometer in case of 2 tungsten.
Okay, thank you. I hope it was clear for Marendra. We have a second question, and I would like to ask you, please answer short if possible. Okay, so the question is, okay, regarding the saturation of S parameter, is there any ion mass dependence? We see that for helium ions at very low dPa, a saturation of S parameter. But with hydrogen, even at 0.65 dPa, saturation does not happen. This is the question.
Yes, I'm sorry, but I showed some helium irradiation, but no hydrogen. So I don't see what. Maybe I missed something. Maybe I should come back.
Yeah,
to
maybe these were not your results. I guess. Yeah, you did not show any hydrogen.
So of course, the damage will depend on the nature of the ions.
Yeah, sure.
And, for hydrogen, we expect to create less cascade, of course, and it's not it should not be comparable to a self-irradiated tungsten, the damage that could be created. So we didn't perform any experiments using hydrogen, or very few. So I'm not able to answer very precisely to this question. I'm sorry.
Yeah, okay. I think we can skip this. So I would like to thank you very much for your nice talk.
Thank you.
Okay.
Thank you.
And yeah, and so we cannot directly come to the summary because we still have the talk of, where is it? Of Taras. Okay. Taras Kavetsky. Yeah, here it is. Taras, actually, we will do it in such a way. I hope you can, yeah, you can hear me, of course. We will do it in such a way that the people from the organizing committee, they will show up your slides. You can see them here already. So, and if you go to the next slide, you just say next slide, and this works. I'm sure it works. You have 46 slides for 15 minutes. So it's some kind of a video, or I'm not sure. So so please be in time. You have 15 minutes, including discussion. So I think 46 slides are okay.
Okay.
To show. Okay, but the floor is yours, please.
Are you hearing me good? Are you hearing me?
Yes, I can hear you.
Okay.
Okay.
Okay. So the title of presentation: 3-volume characteristics of photocrystalline polymers as holding matrices for construction of parametric enzyme biosensors. Please, next slide. The content of the report, I will talk about lacase, why we use lacase for parametric biosensor, why we use firstly organic and organic resin-based polymers, these polymers with metal particles, with the clusters, also with titanium dioxide nanoparticles, and finally we check photocrystalline polymers for biosensors and conclusions. Please, next slide. Why biosensors in lacase? Because you know, due to technogenic pressure on the environment, the pollution of wastewater is highly problem in the world, and one is innovations is the solution of this problem is creation of highly sensitive biosensors for analysis of level of wastewater pollution. One of pollutants, such as bisphenol A, xenoestrogen, has or carcinogens, has toxic effect on the human and animals, and this problem is very, very serious. And we use lacase. Why? Because lacase is as enzyme is can remove the microproteins from wastewater. The next slide. And also this enzyme has possibility to direct transfer of electrons, and thus we can construct the mediatorless biosensor of third generation. So we constructed these biosensors using real silicate matrix for the first time using the case. Next slide. Why we use real silicate matrix? Because this is highly transparent and very flexible and very wide practical applications. Next slide. It is easy to modify this matrix, for instance, with chalcogenide clusters as particles, and you see presentation here as the picture of this real silicate modified with chalcogenide clusters. Next slide. We test this real silicate. This very changes free volume of after modification of chalcogenide clusters. Next slide. And this real silicate matrix, volume matrix, is very useful as a dispersion media for luminescent salt, ion conducting lithium salts, semiconductor metal nanoparticles, and others. And for the first time, we use this real silicate composites for construction of anthromatic biosensors and for immobilization of lacase. We know from literature that the biocompatibility of this matrix is dependent on the crystalline density. Next slide. And we also feel that the changes in crystalline density and free volume may affect on the biosensor's characteristics. Next slide. So here we constructed these biosensors using real silicate matrix, and what we found here, we have very good results. For instance, when we see Michaelis Menten constant, is efficiency of direct electron transfer from enzyme to electrode, we found that the value is 0.125 millimole to a BTS. Is even lower than the lacase for natural lacase from Prometheus vesicle as 0.28 millimole. It means that we have high efficiency of direct electron transfer in this biosensor using real silicate matrix. Next slide. When we compare the biosensor's parameters, we compare with real silicate pure matrix with matrices chalcogenide phase clusters, and we found that the sensitivity of biosensors increases in 40 times. Next slide. Using positron elevation spectroscopy, we studied 4 polymers as fresh, aged, and these clusters fresh and aged. We mark K0 and K4, fresh and aged. When we compare here for K4, for K0 fresh sample, we have one indicated with a glass transition temperature Tg, but for after Ag we have double Tg, and a little changes in a little decrease in the free volume for after Ag, like shrinkage effect. Next slide. When we compare with the Brazil matrix with chalcogenide clusters, K4, in case of K4 fresh we have double Tg, but in the case of H sample we have also double Tg, but we have some hysteresis in heating and cooling. Next slide. After evaluation, the positron elevation parameters, we found that the largest difference in thermal expansion coefficients below and above Tg is observed for K4 fresh sample. Here, yeah, next slide. Also, the similar results was obtained using swirling for these 4 matrices. Next slide. When we compare, we see that between 4 polymers, K4 fresh samples has the largest availability or the lowest crystalline density. Next slide. So comparing both pulse and swirling results, we found some agreement that the larger changes in microscopical free volume below and above G for CAFO fresh, also the highest availability or lower crystalline density for this sample using swelling experiments. Next. After checking the biosensors parameters, for polymers, we see the key values decrease gradually when we move from K0 to K4 fresh H sample. Next. But it is interesting to analyze biosensors parameters. When we compare the K0 fresh and H sample, this is pure Brazil matrix, we see that 2 times biosensor sensitivity increase after 1 year after preparation aging. Also the same when we compare K4 sample with chalcogenide clusters, we see that about 2 times biosensor sensitivity is larger for this H sample. But when we compare K0 H sample with K4 H sample, we have changes in the 40 times sensitivity, larger for K4 H sample. But when we compare K0 fresh sample and K4 fresh sample, we have increase in sensitivity in 50 times. So K4 fresh sample shows the most remarkable changes in the sensitivity of biosensors. Next sample. Next. Again, when we check the pulse parameters, we see that for this sample, we have the larger changes in microscopical free volume. Next. Next, and also the highest availability. So we made local conclusion that we can control the network properties, controlling the network properties of polymer matrix. Probably one may control the functionality of biosensors based on the polymer matrix. Next. Here we prove out the concept that incorporation of gold nanoparticles should increase the sensitivity of biosensors, and we add gold nanoparticles to our Brazil matrix. Next slide. We use, here is the IFM and SEM analysis and GMM analysis of gold nanoparticles. We estimated the size of nanoparticles above 200 nanometers. Next slide. And when we compare pure matrix, this is Brazil with composite chalcogenide glass. This is actually K4 matrix with without and with gold nanoparticles. We found that biosensor sensitivity increased with adding of gold nanoparticles, as it was expected. Next slide. Also, when we evaluate the parameters of our biosensors, we found that we have improved parameters comparing to literature data. So we actually constructed the biosensors with the best optimal parameters. Next. The same situation we found using titanium dioxide nanoparticles as we use a Nafion membrane. Next slide. We don't see a little difference between values of Km, 0.32 and 0.34. But next slide, next slide, when we compare biosensor sensitivity, we found that with adding nanoparticles, titanium dioxide nanoparticles, biosensor sensitivity increased in times. So after this correlation, we think to study photocrushing polymers, another type of polymers, and we focus on the epoxidized lines oil polymer with bisphenol A diglycid ether as reactive diluent and photoinitiate. Next slide. Here is the chemicals of these our photocrushing polymers used. Next slide. We use polymers in 30 molar percent of Rd and 30 molar percent of Rd, and based on the epoxidized lines oil. And here we study swelling results and found that this first polymer, EO10Rd, has the lowest availability, higher crystalline density. Next slide. Also, this polymer shows the larger hysteresis between heating and cooling compared to EO30Rd. Next slide. When we when we return to the Brazil matrix, we found that for K0 fresh sample, where the for H sample, where the sensitivity of biosensors is qualitatively the larger, also we have some hysteresis in heating and cooling. So some agreement with photocosmic polymers. Next slide. Next, we prepared biosensors using graphite electrode. Next slide. Next slide. This is parameters of biosensor for evaluation. Next slide. Here we have the econometric results for two polymers, and from these curves we estimated biosensor sensitivity. Next slide. And we see in the case of first polymer, IL-10RD, we have the larger sensitivity of biosensors compared to IL-30RD. And reproducibility of our biosensors is very good. We checked the three independent econometric studies, and the changes was between 0.5, 0.7. It is in the normal. So this biosensors is a good reproducibility. Next slide. So when we compare these polymers with PAL results and the biosensor results, we found that for this IL-10RD, we have again the largest changes in microscopical free volume, below and above Tg. Again, we have for these biosensors the largest sensitivity of biosensors and even larger of range of linearity. So again, correlation when we have the changes, larger changes in microscopical free volume, we have the larger sensitivity of biosensors. Next slide. After that, we studied the other photocosmic polymers based on acrylated epoxidized soybean oil, ESO, and using trimethylpropane triglyceride ether RD1 as reactive diluted, and also we use photoinitiator TMPR, and also we use vanillin dimethyl VGM. Yes, next one. So here, when we compare our photocosmic polymers, two polymers, ESO-VDM and ESO-VDM with photoinitiator, and also our epoxidized oil LO10RD with photoinitiator and LO with photoinitiator. What we found, in this case, we have the larger free volume, and also in the case of ESO-VDM, we have the larger free volume, and also we have larger changes in microscopic free volume below and above G when we calculate the slopes. Next slide. Here is the this picture shows the larger free volume is between compared three polymers. We have the largest free volume in ESO-VDM. Next, ELO photoinitiator. Next, IL-10RD photoinitiator in there, and the next ESO-VDM DMPA. Next slide. When we compare biosensor sensitivity, we found the same results as previously for previous polymers. We have this biosensor sensitivity is larger for ELO PA photoinitiator is smaller. IL-10RD1 photoinitiator is larger here, and the largest biosensor sensitivity is ESO-VDM. And for ESO-VDM with photoinitiator, we cannot use this material for biosensors as we cannot dissolve this polymer to construct the biosensors due to very high cross-linking and very fragile polymers. And also we can use these three types of polymers for construction of biosensors. And when you please back for previous slide, you see the same series as the VDM, largest free volume, next ELO photoinitiator, smaller free volume, and then IL-10RD1 photoinitiator, the smallest free volume. So we have very nice, again, correlation that larger free volume of polymers and larger changes in microscopic free volume leads to the increasing the biosensors, improving the biosensors sensitivity. Next. Next. Next slide. Next slide. Next. Shortly, in conclusion, before. In conclusion, we conclude that the larger change in microscopical free volume volume about G, as well as the larger values of free volume holes for the investigated polymers probed by positron relation, the larger sensitivity of biosensor is obtained. Finally, as a result of the research carried out, one may suggest about finding a more possible master parameter related to free volume holes in polymer network for controlling the functionality of aromatic enzyme biosensors that would have a significant impact and application in analytical biotechnology. Thank you very much for the attention.
Yeah, so thank you, Taras, for your talk. We did not get any questions. I also have no questions, maybe due to the fact that your topic is not really, does not really hit the character of PSD conferences. But anyway, I would like to thank you very much for your talk. Now it worked.
Thank
So
you.
I can say that, yeah, Taras, I think now we have seen all the results. The only talk was from Alexei, where the audio quality was really too bad. But I mean, all the others, 50, I think, talks were really fine. So actually, no problem. And I have to say that the audio quality was even better than in many lecture halls. And also the video quality was very, very good. So it's no problem to follow. So we have just one talk still missing, and this is the talk of Akira Uedono, who is already seen here. Akira will give us a summary of our conference. Akira, please.
Mute is off. Can you hear me?
Yeah, yes, we can hear you, no problem. But we don't see your slides yet.
Because the organizer do not give me the switch of sharing the display.
Okay, yeah, okay.
I'm just waiting.
I'm not sure whether I can do it. Maybe yes. So
okay,
okay, now. Okay.
Here it is. Go ahead.
Okay.
Then
go ahead, please.
Yep. Okay. Yep. So thank you very much for opportunity for giving me a chance to summarize PSD20. That is a great honor for me. Well, in this summary, let me talk about briefly the short history of PSD20. Then let me talk about future positron static defects. That is just my opinion, but it might be interesting for you. So PSD20 was originally planned to be held at the DAE Convention Center. That is a residential colony of BARC Park on March 22 to 27th last year. Well, this is a DAE Convention Center. I took it from the internet. It seems to be very nice, very, very nice facility. And here is a Google map. This is the DAE, and this is Chhatrapati Shivaji International Airport, BOM. So according to the Google, foreigner can go to the conference site by using the car, taxi, 30 to 60 minutes. So it must be a very convenient location. Well, it depends on the traffic jam in Mumbai, of course. And here you can see the original program for PSD20. So March 22, welcome and diner. And the next day morning, well, actually, my talk was set to be just after Professor Claude-Lieberg's talk. So that is actually very nice for me because I am going to give a talk on the first day of the conference morning. So this means that after my talk, I'm free. I'm very much relaxed. I can enjoy everyone's talk. and also I can enjoy the very, very nice Indian foods. You know, Japanese are very much like the Indian food. And actually, I have one thing I want to do in Mumbai. So that is my personal ambition. So my ambition is catching a train in famous Mumbai. I was planning to do it not during, but after the conference. So here you can see a lot of people doing this. So I also want to do this because that must be the once in my lifetime event. So if I can survive this, so I can tell this everyone. So I did this like that. But if I said I want to do this, so everyone says that please do not do that. It must be very dangerous, etc., etc. But at that time, I have to say that you should not underestimate a skill of Japanese using a train in rush hour. So this is Tokyo, I think. So we Japanese doing this every day. So you don't have to worry about me. However, as we all know that 15th May, just a week from the conference, we obtained a very sad email. Email says that we organizer now at the final stage of our preparation of PSD 20. However, with a very heavy heart, we are forced to announce the postponement of the PSD 20 because of the COVID-19. That is a very sad email. But at this stage, there is still the possibility to have a face-to-face conference, I think. So I know that the organizer committee are discussing about postpone, and there's a certain possibility if we delay the conference up to June or October, we still have a possibility to get face-to-face PSD 20. However, 20th August, we again very sad email. Under the prevailing circumstances, it would not be possible to hold PSD 20 with a physical gathering of the participants. So we organizers have tentatively decided to hold a virtual meeting in March 2020. So this is in PSD 20. But I personally surprised that the organizer decided to defund the registration fee paid for participating in PSD 20. I believe that many money fund is already used for preparation by local organizer, but still organizer want to refund the registration fee. Well, that must be very difficult decision, I believe. And I have another concern. So we have a problem due to the local time difference if it is international conference. That is always have a big trouble if the conference is international. And of course, PSD is international conference. But as a result, this is a time schedule program of ePSD 20. I found that the present title's local time is said to be very reasonable. So I believe that the organizer did a very careful arrangements of talks during the ePSD 20. And also, the PSD 20 was broadcasted by WebEx and YouTube. And I found that the YouTube videos of especially session 6 were seen 160 times already, and still increasing. So number of participants would be higher than that is shown in the WebEx, I think. So I would like to thank advisory and organizing committee and the local organizer especially for the effort of first preparation of physical PSD 20. That is the original one. Then very difficult decision of the postponement and conversion from face-to-face to web-based conference, plus refund, don't forget. And of course, running EPSD20. Well, in many conferences, the person who summarized the conference give a prize to the best performer. But for this PSD20, I would like to give the applause to the local organizer. If you agree with me, please show your applause. Thank you very much. Yep, we have a lot of applause. Thank you very much, everyone. I'm still working, but let me continue. Thank you very much. So let me overview EPSD20. Here you can see the number of talks given by each country. India, the top, and Germany, Italy, Poland, USA, and other countries. Well, I found that the number of India is the highest. So this is probably due to that the original PSD was organized by Indian local organizer. Well, I think that is half true, of course, but half wrong, in my opinion. So in order to confirm this, I calculated, I made a database, yes. The paper related to Positron and defects using Web of Science. The total number of paper which somehow related to Positron and defects is around 5,500 at this stage. Then I found that the top country which produced the paper which related to Positron and defects is China. Yes. Then Japan, Japan, writing the paper which related to Positron and defect, I don't know. And Germany here, United States here, then India. Here, this is India. So my opinion is India is the top of second group. So foundation of the Indian Positron research is solid, I'm pretty sure. Therefore, there's no surprise, definitely no surprise if the high number of talks is given by Indians in EPSD20. So that is my opinion. Now, let me categorize the talks given in PSD20. So, well, the paper or talks which related to metal is top, and instrumentation, metal oxide or ceramics, and other materials, semiconductors, mesopolars, and polymer, previous one. Well, because I am a researcher, if I prepared two figures, this one and this one, of course, what I want to know that the correlation. So what pop in my mind is that is there any relationship between study of metal and Indian Positron researchers, or Indian Positron researchers especially like to study metals? So that is my question. So I made another figure. This is a paper given at the ICPA 17. Well, original data was taken by Professor Claude Riebel and Professor Jean. So this is ICPA, and this is PSD20. And here is a metal, and metal, oxide, ceramics, etc., etc. Then polymer. Well, polymer is included because that is ICPA 17. Then instrumentation. Well, so the tendency is completely same, in my opinion. So, and also it seems that the Positron researcher likes study of metals, which causes a change of the comparison name from PSSD to PSD, as mentioned by Professor Claude Riebel on the first day. So that is the relationship. So let me talk about my personal impression of PSD. At PSD, so many presentators use not only conventional Doppler Brodin profile measurements and also lifetime measurements. But also, they always use a constant Doppler spectroscopy, including making a ratio curve and SW plot in order to identify what they observe, and monoelastic positron beam, intense positron beam, ARCA, new challenge for theoretical calculation, and many combinations using other characterization techniques such as XRD, TEM, SEM, BET, neutron beam, SANS, etc., etc. Then we are discussing very much detailed material science. Well, in my humble opinion, the quality of the talks, all the talks in PhD 20 are definitely higher than those in any positron conferences held 10 years ago. Yeah, I'm pretty sure about this. So, however, let me select one talk which appeared in PhD 20. That is a new topic. So in the case of new topic, it is very easy to select. I believe everyone agree with me that a new topic presented in PhD 20 is definitely antimatter wave interferometry, given by Professor Raphael Ferragut. Actually, this work selected by Physics World as top 10 breakthrough 2019 IOP publishing. Well, this is already mentioned by Professor Raphael Ferragut in his talk, but well, that is a very good work. This mark is Japanese, means a very good work in Japan. This is very familiar for Japanese. So, as mentioned by Raphael Ferragut, of course, this technique has a close relationship to depth, high energy positron diffraction, and low energy positron diffraction. So I imagine that in the future, the positron interferometry with positron microscope using intense positron beam facility would be installed in the facility and could be a very important tool for the surface physics. So I would like to thank Professor Ferragut to make a pass which lead to the new holy grail, that is positron interferometry. So this is Raphael and the positron researchers, and this one is optics of antimatter wave interferometry. So that is my impression. Now, let me talk about my personal opinion, the future of positron study of defects. I'm not talking about the future of positron study of defect conference. No, I'm going to talk about the research field named positron study of defects. So I already make a database. So I made one figure which shows that the number of publications which related to positron and defect as a function of time. Well, I still do not know, but the number of papers which somehow related to positron and defect suddenly increased 1990 here. Well, 1991 is ICPA 900, but I am not sure the relationship between this and this. And anyway, that is increased like this, then in my opinion, still increasing. So this fact suggests that the PSD as a research field is producing important, meaningful results and contributing our society. And which journal publish the paper concerning positron and defect? I personally very much surprised that the number one journal is Physical Review B. The second is my favorite journal, Applied Physics. And third, Journal Nuclear Materials, Applied Surface Science, and NIM-B. So they are all high quality paper, in my opinion. So PhD researcher, these facts suggest that, have published their works from very high impact journals. So I believe that for young PhD researchers, This must be very important. So here is my message. For young participants in the PhD conferences, Positron study of defects is very good research field. Please stay this field and keep producing good works. Then let's meet next PhD. Well, I have heard that the location next PhD has not been fixed yet. And the PhD committees is now working on it. And I heard that there are two applicants, India again, and Italy. And it will be announced later. And do not forget that my ambition has not been fulfilled yet. I must go to India in the future. Well, that is my summary. Thank you very much.
Akira, that was great. This was really a great summary. Thank you very much. Yeah. So before returning the chair to the organizers, I just want to mention, yes, there are two applicants, and we will have maybe a month from now, we will make an online meeting with the International Advisory Committee and also with the two applicants to decide where PSD 24 will be held. Yeah. So I think I just have to say that the organization was great, and I did not expect it so beautiful and so easy and so smooth. Yeah, this is maybe the last thing to say, and I give the chair back to Pujari, to Professor Prade Pujari, I think, as the organizer of the conference. I think, or you can decide. Okay, thank you very much, and then this is my goodbye.
Thank you, Professor Reinhard. Thank you for conducting the session so well. And I must thank Professor Akira Uedono for a very, very nice summary, of course. And I thank him especially for he had so many good words for us. And I promise him that we will certainly have some event in Mumbai so that he gets the opportunity to ride the train. And I promise him I'll join him that time, because that will be a challenge for me too. Now we're at least at the fag end of the meeting, and I'm very happy that actually we could do it very smoothly. But we did a lot of exercise. This room is like a control room. Actually, we have 4 laptops actually connected to the net, and I mean, my colleagues worked out all the details, like smaller details like giving the time slots convenient to like what Professor Akira Uedono has pointed out, that we made sure. So the conference is such that it is not really, the sessions are not based on the topic, but the sessions are based on the location. People being in a particular location, and the timing thereof. So that is a strange thing you must have observed. So I'm really very happy, but I'm also sad that I see all my friends on the screen, but I cannot sit with them and have a cup of tea or enjoy dinner in Mumbai and the good food in Mumbai. I mean, we had made fantastic arrangements. We had made, let me tell you, at least since you have not been able to do it, there are very special arrangements or social programs. We had a special heritage tour of Mumbai. And this was very unique because I've also had never the opportunity to do that. I thought that I'll, join the, I mean, together I'll also have, I know Mumbai, we see Mumbai, but Mumbai from the, from the perspective of a tour or walking tour and the heritage tour would be very, very special. And of course, there is still, things are not good enough to do that even now. But in future, maybe you will get the opportunity to enjoy that facility. So finally, I thank my team members, especially Dr. Kathi Sudarshan, the convener. You can come here so that others can see you. And Priya Maheshwari, who is the secretary and who actually was instrumental in bringing PSD to Mumbai, thanks to Professor Reinhard. At the last PSD meeting in Dresden, and Sandeep Sharma, who is a treasurer, who is arranging money, and everybody else. Please come join me, come behind me, and so there are some new positroners also. This year a new boy has joined. Yeah. So I thank all of them. We come here. Yeah. I thank all of them. This is the Positron team from Baba Atomic Research Center. And thank you very much for being there. And yeah. And you could switch on your video so that you can have a and mic also you could switch on. Enabled. Everything is enabled. Now everybody can speak and everybody can come on live. Yeah. And we can have a photograph.
Bandwidth issue. That's why you are sitting.
All videos going Okay. So thank you very much and namaste from India.
Thank you.
Bye-bye.
Thank you.
Bye. Look forward to seeing you in Mumbai soon.
That's all.
Bye. Thank you very much. Bye.
Thank you.
Thank you very much, Pujari.
Good. Well done.